Hello and welcome to Energy Connect's third webinar in partnership with Schlumberger. Thank you so much for joining us, and we're delighted to bring you this live interactive webinar as Schlumberger present Cameron Ram Technology, What's Inside Matters. I'm Julian Walker, the Editor-in-Chief of Energy Connect, and I'm delighted to be moderating this live session. Good morning, afternoon or evening, wherever you are. I know we have a global audience joining us for this webinar. We are really happy that you have taken the time to be with us today. Now, before we get started, I just wanted to bring to your attention the screen in front of you. As you can see, it is quite a dynamic screen, and you can move it around as it has really been designed for your ease and comfort so that you can be fully involved in the webinar. So do please move the screens around and get comfortable with the layout that works best for you. You can also alert your friends and associates because we'll be live for the next hour, so they can join us if they haven't signed up in advance. Both our experts will have a short presentation, after which we will open up the webinar to questions from the audience. We really want you to get involved, so please do put your questions to our experts throughout their presentation, which I will then ask both speakers after. Finally, you'll find some resources and research from Schlumberger and Energy Connect that you can download and digest at your leisure after the webinar on your screen. Now we are all done with the main housekeeping, let's get down to the business of today's webinar looking at Cameron's RAM technology. I'm delighted to welcome two experts from Schlumberger to discuss Cameron's RAM technology. We have Matt Givens and Sam Baim. Thanks for joining.
Thanks for having us, Julian.
Thank you.
And you can see their full bios on your screen at whatever you want. Now, what I really want to do is to get this webinar started. I know all of you have signed in to listen to our two experts and to see what they have to say. So to kick things off, we're going to start with Sam, and then Matt will carry on the presentation halfway through. Sam, I leave it in your hands.
Thanks, Julian. I'm going to kick off our conversation today with a light overview of our product portfolio. So to start, the most basic offering we have is a pipe ram. The pipe rams seal around a single fixed size, but they're available for all commonly used sizes of tubing, drill pipe, or casing. We have ram packers that lock in place so they're not dislodged when you have well flow when closed, and the ram packers themselves can be swapped out. So we'll be talking a lot about elastomers in this presentation, and it's good to note right at the very beginning that there's different types of elastomers that you can change out on your ram blocks, like our CamRam or CamRam 350 style. The next ram is a variable bore ram packer, or a VBR, that you see on the screen. It has the same key features as a pipe ram, such as the ability to lock in place and seal the well when closed. But instead of a fixed pipe size, the VBR seals on a range of diameters. There's a lot of exciting new developments in this space, so we'll dive a little bit deeper into the VBRs on the following slide. We have shear rams that seal, and we have shear rams that also shear but do not seal. The shear and seal rams are generally referred to in the industry as blind shear rams. The most popular types of blind shear rams that Cameron offers is the SBR, CDVS, and DSI. The key product to highlight in this space today is the DSI. The DSI is available for surface-based equipment, such as Type U BOP stacks, and subsea-based equipment, such as TL BOP stacks. This presentation will go into detail about the DSI features, the shearing style, achievements it's had, and offerings for the different types of environments, like subsea and surface. But as I noted, there's also non-sealing shear rams, and the intent of a non-sealing shear ram is to focus on shearing larger tubulars. Cameron has historically offered the super shear, but our latest and greatest offering featured on the slide is the broad shear. The broad shear has even further improvements in shearing performance. It's the industry's only BOP that shears heavyweight casing, tool joint, hard banding, off-center tubulars, wire, electric, slick line, and braided cable. Again, the biggest difference here is that it's a non-sealing ram. It exceeds the requirements of the Bessie well control rule, and the broad shear's claim to fame is its ability to reliably shear casing diameters up to 17 inches and off-center tool joints. Our RAM BOP portfolio in front of you boasts 37 unique configurations of model, size, and pressure rating, ranging from 7 inches to 26 inches and 3,000 to 25,000 PSI. So some of these technologies may not be available in the size that you're specifically interested in, but it's always worth reaching out to your local Cameron sales representative and reaching out to us to see what's available to meet your needs or what development opportunities exist. We'll get into the specific brands next for our most popular BOP sizes and pressure ratings. So as I mentioned earlier, there's a lot of new exciting things in the VBR space. In general, though, VBRs provide a seal, again, to a range of diameters. For example, the 1310K Type U VBR on the screen is suitable to seal on pipe from 3.5 to 5.5 inches in diameter. We'll talk about the 13-inch VBR, which was designed for high-temp applications, and an improved 18-inch VBR designed to provide minimal extrusion and much better hang-off than its predecessor. Traditionally, because we need to seal on a wide range of pipes, it's harder to get an extreme temperature range between min and max pipe sizes, which is why you normally see a smaller range of pipe capability. But our 13-inch high-temp VBR features uniquely designed inserts in a new elastomer material. It enables it to withstand extreme heat for challenging well sites. And during qualification, the packer greatly surpassed the minimum API extreme temperature holds. So for customers, this translates to having more time to make informed decisions during well control event while the pressure is stabilizing. It also allows our customers to use a larger window of tubulars across the BOP at an increased range of operating temperatures. Talking about the VBR's design in a little bit more detail, I can let you know that we added a significant number of anti-extrusion inserts and an extra main insert to the body, to reduce the extrusion gap when sealing under high pressure. That main insert geometry is also modified for ease of manufacturability and to ensure the VBR centralizes the pipe during closure. There's also a modified retainer plate to have hard facing on the surface, which prevents extrusion gaps and cavity scarring. The 13-inch BOP is primarily used in onshore surface applications, so we reached out to customers in those regions during development. We leveraged input from clients in both Middle East and North America geographies, and the chart on the slide there highlights all of the API 16A 4th edition achievements. At 300 degrees Fahrenheit, we achieved an 8-hour extreme temperature hold on the 5.5-inch max mandrel and an 11-hour hold on the 3.5-inch mandrel, which is quite significant and greatly surpasses that API minimum requirement of 1 hour. Besides extreme temperature, though, the VBR also performed exceptionally well at low temp, so it reached that 30 degree Fahrenheit mark, which again, as noted, it's very difficult to get a good low temp and a good high temp in a VBR because of that range. We exceeded the API fatigue cycle requirement by 50 cycles as well. And in parallel with the 13-inch VBR development, we created a new and improved 18-inch VBR for the 3.5 to 6 and 5/8 range. The main benefit from this 18-inch redesign was an increase in hang-off capacity for ultra-deep water opportunities. It was qualified to hang off on 1.1 million pounds on its largest diameter. I also mentioned that we created a new elastomer for the 13-inch, which is utilized in that new 18-inch design as well, for the packer and for the top seal. So when you look at those API test results, you'll also see a high number of fatigue cycles achieved in the 18-inch space. So up until now, we've really only been discussing sealing, where we close the ram and seal on a pipe. But the conversation for the next few slides is going to expand to shearing in our shear portfolio. There may be times when a well control event requires you to shear your tubular and create a seal. So when we talk about shear rams, customers often ask us, do you have a ram that can shear this pipe? And the answer is usually it depends, until we have a better understanding of your system and your constraints. The three biggest variables to consider related to shearing are the tubular that is to be sheared, the BOP bonnet, and the shear ram itself. So our customer or the well engineer picks a tubular based on the well design, so this variable to us is a fixed constraint. That forces us as an OEM to think about the ram design and the BOP bonnet capabilities. So when thinking of the ram, we consider the design profile of the blade and the force required to shear the tubular. When thinking about the VOP bonnet, we consider the operating pressure and the force output requirements. So in that case, the question might be, can my max operating pressure of the bonnet handle the load required to shear that tubular with that ram? So if you look at that wheel on the slide, it addresses those three main variables. Once you start to increase the complexity of the tubulars, we get into new technology conversations. So our legacy blind shear ram, the SBR or shearing blind ram, is one of those legacy products. That it's possible it can physically shear a new tubular spec, but the existing bonnet might not be able to handle those shear forces and shear pressures required. So this will lead us into new developments like the DSI, a new shear ram that we'll talk about in more detail, and a 5K bonnet that Matt will touch on with higher operating pressure. So this will accommodate new tubular or new well program specifications. So there are a lot of different varieties of blind shear rams available in the market. Cameron's latest technology in the blind shear ram space is housed in the DSI. Effectively, all DSIs are capable of shearing wireline, whereas other blind shear rams like the shearing blind ram or SBR mentioned previously are not. The SBR is incredibly popular, and it's an offering that may definitely meet your needs, but the DSI is next level. So the DSI next level shearing technology has increased shearing capacity and the ability to shear wireline. When you think about offshore environments or large bore BOPs, we also have the DVS and CDVS offerings, which may be capable of shearing wireline, but are restricted by wall thickness due to geometrical limitations in the shear ram itself. So the 13-inch and 18-inch DSI products featured on the screen, we'll talk about how the development achievements and how they meet our users' needs or exceed the regulations outlined by BSEE's 30 CFR 250 regulation. That regulation requires operators to have one ram that can shear and seal items ranging from wireline to a preset list of tubulars. So some key features of the DSI are that they were developed to shear multiple tubing strings regardless of the orientation to the center line of the wellbore, and they have an interlocking blade profile that provides the capability to shear and seal against wireline and braided cable. They can also shear a larger diameter tubular than the SBR due to an increased blade width and thickness. The ram block design, with that larger width of the bore, provides full wellbore coverage. Upon completion of shearing also, the lower fish is housed in a vertical pocket, while the blade face seal provides a seal between the horizontal faces of the upper and lower blades. So for surface applications, we offer a DSI specifically in 7-inch, 11-inch, 13-inch, and 16-inch sizes as noted on the slide. The 13-inch was our first shear and seal ram designed from scratch to specifically meet API 16A 4th edition criteria and customer requirements. As shear rams are your last line of defense against catastrophe, the ability to shear and seal is a core focus of our pressure control equipment, which is why Cameron puts a huge emphasis on shear testing and the data that we can provide from it and get out of our customers and meet all those needs. In order to create the next generation of shear rams, we utilize a combination of advancements in engineering simulation and modeling, real-world physical testing, and elastomer characterization. So this allowed us to bring these rams to market in a much faster timeline than previous developments. Cameron's been leveraging the larger Greater Schlumberger organization as well and made significant advancements in digital technology that go beyond just generic FEA results. To enhance its product design through these tools, again, that 13-inch from the ground up was one of the quickest developments we've ever had within a year. So the DSI blind shear ram designs produce the slowest shear pressure during operation out of any of our 13-inch shear and seal rams in our portfolio. So when you're looking at the 13-inch SBR versus the DSI would have the lowest shear pressures. For customers, this translates to a reduction in overall rig system complexity. So it lowers the usable volume requirements, which means you need a lower number of accumulators, smaller skid size, and smaller reservoir size. The 13-inch, 11-inch, and 16-inch were all ground-up designs using that methodology and technology not previously used before. This leads to increased wireline capability and able to shear the BOP within the BOP limits defined by that wheel earlier. I'll lead it off to Matt now to take over on the subsea side.
Super, thanks, Sam. And I think we're going to go over to Matt, who I think might be on mute.
Nope, I corrected my glitch there, Julian. Thanks very much. So like Sam was talking about, the surface applications of 7 through 16-inch UBOPs are a great design improvement to one of the world's legacy BOPs that's been out there. When we try to transition to subsea programs, like the 18 3/4 15K, or even some large bore jackups that might be using an 18 3/4 15K BOP, we had to take all of the lessons learned from our smaller surface program and apply those to the design of the larger ram. We also incorporated the design technology that's utilized in our existing CDVS2 or cable double V shear ram, and other developments that aren't quite ready for prime time yet. And brought those together to a ram that's now capable of shearing from wireline up to 14-inch casing. So what this improvement is, if you look at the existing CDVS2 ram that's used in our subsea BOP stacks today, that ram was limited from wireline up to about 11 3/4-inch casing. To get to that 14-inch size, we had to widen the ram profile and make some changes to how it comes together. We also wanted to remove restrictions in the sealing technology where we had a problem with a fold-over pocket. Effectively, when the two rams come together for shearing, we needed to move the lower fish away. And where that's important is when you're attempting to shear and seal on a tubular that is either landed off intentionally in the BOP stack or is stuck in the bottom where you're still in a drilling operation and the lower pipe can't move down. So that feature allowed that technology to go. But what it did was it provided a geometrical limitation to the tubulars that we can shear and seal with the ram. So in the DSI family, both for surface and for subsea, we removed that geometrical limitation, and now the shearing capability is limited purely on diameter and then the amount of force that we can provide as it comes through. Because we wanted to shear some really heavy tubulars and how that all comes into play, we needed to also change the manufacturing way that we build these rams. Traditionally, all rams in the industry are made through a wrought forging process. Effectively, you pour molten metal together, you hammer it down, and you get a general shape and a texture or material properties that you're expecting, how thick and how strong that material is. To achieve these heavier weight, larger diameter tubulars, we went with a process called hipping or hot isostatic press. Effectively, we're using a powdered metallurgy process with heat and pressure to compress the ram into shape, which gives us a much better through properties of the ram. It means now we don't need to have 5 heat treat cycles to get the blade portion of the ram to be really strong, but the body of the ram to be less so. By doing this, we're able to shear a 6 5/8, 64 pound per foot UD 165 tubular. Now we do that at an extremely high pressure, which means that we need to work on some other technology we'll talk in a moment. linking it to the wheel Sam presented. But we've also been able to get things like the 10 3/4 casing, 14-inch casing, and all the way back down to slick line, wire line, and electric line, meaning that these rams now exceed the requirements of the U.S. government's Bureau for Safety and Environmental Enforcement Code of Federal Regulations, or the BSEE well control rule. Like we mentioned, the rams are available today for the 18 3/4 15K TL, and soon for the 18 3/4 15K Evo. Those are just models of the BOP. If you have one, you'll know it. If not, it's okay. But so that's kind of the DSI ram. As we talked about through these, Sam was talking about elastomers. Because we needed the larger range of shearing, we also had to address the temperatures that come, and we had to reduce the size of the packers on the side to clear that larger tubular in the existing wellbore we have. We accomplished this by editing our compounds we use, the way we mold it, and the way we build it into the ram. But we were able to achieve API 16A, or the American Petroleum Institute Specification 16A, 4th edition PR2 at 30 degrees Fahrenheit low, 200 degrees Fahrenheit continuous, and 350 degrees Fahrenheit extreme temperature rating. So we were pretty excited about that. And these rams are fully backwards compatible to the existing BOP you have today. There's no change required to install these. You open the bonnets up, install the new rams, and go to town. But like we talked about, as we increase the shearing capability of the ram to match the customer's tubular requirements, or the tubulars going to be used in the field, we enter into that third section of the shearing variables that Sam introduced a few moments ago, which is really the BOP's capability. Now here we'll refer to it as the bonnet, but this is just driving effectively how much force can you provide in the same package to get the ram to shear the tubular as required. What you see here is the layout of our new 5,000 PSI rated working pressure tandem booster bonnet that would be applied for shearing and sealing applications on an 18 3/4 15K BOP stack. This bonnet increases the rated working pressure from 4,000 PSI that current rigs use today up to 5,000 PSI, which results in about 30% more shearing force because we did some geometry changes as well. So the pistons are slightly larger and the pressure is higher. So we can get that extra shearing force to get some of these heavy strength tubulars. It uses all the existing technologies that we had in our 4K, but also employs some new seals, designs to give increased reliability and functional performance in the sealing. And it does so in the same weight, or actually slightly less by about 75 pounds than what the existing design did. So in the same footprint, for the same weight, and effectively the same hydraulic volume, we can get you 30% more shearing force to increase the things that you do. Now, much like the ram, this is backwards compatible to a existing BOP stack that would be in the field today, and it actually simplifies the control circuitry because the rigs have a 5,000 PSI control system, and our existing tandem booster was rated to 4,000 PSI, which means we can take out one step-down regulator from 5,000 to 4,000 PSI and just run at 5,000 for it. So we've de-risked a lot of the features, improved the seals, and be able to increase that force. These bonnets are currently in qualification right now at our facility in southern France, and will be available on the market very shortly. But when we go from just talking about shear force, we also need to talk about how we secure the well after shearing. So effectively, you've come to a well control event. You've needed to fire your shear ram or your standard blind shear or pipe ram or variable bore ram, and you want to now lock in the BOP so that it stays closed regardless of any loss of hydraulic power to the BOP. So traditionally, we've used manual lock screws on surface, or even the legacy Cameron wedge lock, which was a large piston mounted 90 degrees to the operation of the BOP or the rams that you could apply pressure to, and it would close in behind and secure the well, effectively keeping the rams from being able to open under pressure. The problem with that is it uses a lot of pressure, and it was only limited to locking on certain size tubulars, which meant that in all operations, you didn't necessarily have the ability to close, lock, and vent your pressure. So Cameron developed the new Rotary Lock. This is intended for surface applications on both the U and UM style BOP. And what this does is bring in the ability to lock on any size, bolt up to the existing BOP. You would either disconnect your existing wedge lock or your manual lock screw and bolt this assembly up. It uses 2 hydraulic lines that's traditionally water-filled or water-based BOP control fluid, but can also be run using oil if you're in certain temperature environments where you're worried about the control fluid being able to address the environmental temperature, not the wellbore temperature, but the air temperature around it to keep from freezing. We've qualified this for 11-inch, 13-inch, and 16-inch U and UM BOPs. It's available today, and as I addressed it, it retrofits directly to the BOP itself. The last thing I really wanted to talk about, though, is, we brought in a lot of technology. We're showing the latest and greatest shear rams from Cameron and why what's inside your BOP matters in your ability to control the well and keep everyone safe and operating. But how we prove that technology before we deliver the equipment to our customers is through a significant amount of validation testing. Now, this testing is basically a critical step in how we ensure the products work for you and how they operate. And we meet or exceed the minimum industry standards that API sets forth in their specifications. And then we also take on board Cameron's internal requirements for design or customer input for what loads they might need us to test. We have an extensive range of facilities around the world. Effectively, every manufacturing facility that we deal in has the capability of doing what's called a factory acceptance test, which is basically we built the product, we need to function it to make sure it's doing what it's supposed to do before we deliver it. But before we even get to factory acceptance testing, we have facilities in the United States and in France that do research and development testing. So this is where we prove the product prior to even approving it for full manufacturing. Here in Houston, we do this at a facility called the Harry Cameron Technology Center, which has 6 large below-ground pits where we can apply up to 40,000 PSI and up to 400 degrees Fahrenheit to the BOP, as well as having a very extensive BOP controls reliability area where we can function test a full BOP control system and do simulated circuitry to model what's on the rig and test for things like water hammer and performance of the control valves. Also, here in Houston, we have a facility at our Brookshire plant where we make all of our proprietary elastomers. And the focus of that lab is really validation of elastomers against the wellbore fluids. So here we can take a sample of the elastomer that we use, test it against any drilling mud that the customer may apply, or even sour gas environments. In fact, for that sour gas testing, we're one of the only facilities in the world that can do full-scale BOP testing against sour gas. So we can fill the bore with the fluid you would see and test that. In one specific test, we actually proved that our elastomers were able to handle 45% H2S at 1,000 PSI pressure and 190 degrees Fahrenheit. And we were able to prove that for 48-hour hold period, which is quite extensive. You wouldn't normally see that in an elastomer. This was a 29% improvement over our existing elastomers that we had at the time. So those are really available today. A lot of this testing was used to validate all of the equipment when the American Petroleum Institute went from 3rd edition to 4th edition. But like we said, we also do this for our own in-house testing and for customer testing. So if there's ever a test our customers need, they have the ability to reach out and we can set up customer-specific tests for shearing and sealing, fatigue resistance, or any specific unique characteristics that well might have. We have the ability to line that test up and perform it at our facilities, which really kind of drives home the importance that it's not just about having the equipment. It's also about having the engineering and manufacturing know-how to support the product and to make sure what gets into the field is important and what we put inside our BOPs really does make a difference to the performance in the field. And with that, Julian, I think that's the end of our prepared presentation.
Yep.
So thank you.
Well, thanks a lot, Matt and Sam. Really great, insightful presentation, covered a lot of areas. And as I said earlier, please keep on continuing to send in questions, and both Sam and Matt will do their best to answer them. I've got one here that, we just you were talking, Matt, there about, testing validation. I just wanted to, obviously this is an important part of the design, and how does Schlumberger sort of determine the minimum test requirements for product?
Yeah, that's a great question, Julian. Kind of go back to that slide. I think I can make that go. The key driver there is understanding what the industry minimums are. So if you're looking at like a RAM BOP, the design specification and standard that the industry follows is API 16A, which will set forth the minimum requirements for temperature to be able to do fatigue resistance, which is how many times the BOP or the RAM can close and operate before it starts to wear out, along with the ability to seal and perform at different operating pressures. We use those guidelines to set the bare minimum. Now, Cameron then applies our minimum on top of that, and that's where we'll come in and say, okay, for the Cameron RAM BOP variable bore RAM, like Sam presented, where we tested to 8 and 11 hours, the industry minimum for extreme high temperature is 1 hour, but Cameron, as a standard, will try to push forward to at least 8, and if we have a desire to go further, we can drive from that. But really, the bare minimum requirement is set by industry standards, and those standards are written by a committee participating from the operators, the drilling contractors, the OEMs, and third parties around the world.
Super. Thanks, Matt. Just got a question here from Chris, just asking them, how does the DSI shear ram differ from the Fairline shear ram, or are these the same? Don't know who wants to take it.
Sam, you want me to take that one?
Sure.
Perfect. So yeah, Chris, that actually is the same RAM. The 18 3/4 15K DSI is the official marketing name. The Fairlane RAM was our kind of, hey, here's our cool project we're working on engineering name that we carried through the development program, which was 2020 through early 2021. And we finished these RAMs and commercialized them to the market in late 2021. So it is the same RAM. Fits in the 18 3/4 15K and runs from wireline up to 14-inch casing.
Great, thanks. And Sam, I've got one for you. During the shear ram portion, you stated that the DSI ram does not have a fold-over pocket. What is that? Just for the audience.
Sure. Yeah. So I know that one can be a little confusing without a diagram, but I will try to speak to it. So the fold-over pocket is a Cameron design feature used in our SVR, DVS, and CDVS family of shear rams. So I don't want to call them older styles, but the ones that are essentially not the DSI. When the tubular's hung off or when it's stuck on bottom and the lower fish does not have a place to go, the fold-over pocket creates an area where the lower pipe can be pushed out of the way while the rams are closing during the sealing function. And then after shearing to engage the seal. So this allows the blades to come together and seal properly. But that's talking about those other designs. That's the SVR and DVS. The DSI does not have that pocket, so it still has the capability to move that lower fish out of the way by engaging the seals in an interlocking blade method instead of the face sealing technology on those other rams. So it's all about the geometry of the ram blade.
Get it. Thanks. Matt, we've got one here for you from Leonard, just saying, obviously, you referenced that rams are validated to the minimum requirements of, he was just, I think, wanted a bit more explanation of, API 16A PR1 or PR2.
Perfect. Okay, so there may be many of you out there that don't know what that reference is to PR1 and PR2. In API 16A for drill through equipment or well control equipment that's used on the well, this is ram BOPs, annular BOPs, hydraulic connectors, and spacer spools that would be part of the main bore of a well control system. There are two now in the 4th edition. There are two performance requirement levels. There's PR1 and PR2. That's 1 and 2. Makes it simple. The PR1 is much more like legacy products. It has less stringent requirements. It's still very secure and safe equipment available for the industry. PR2 takes that to the next level, so it adds things in temperature where we have low temperature holds and extreme temperature, it adds a continuous temperature where we now have to prove that the equipment is qualified to operate in a longer period, sustained period of temperature and perform in that. For all of the technologies we presented today, Leonard, everything is available at PR2. So we have qualified all of the equipment in both VBRs and all 4 shear M sizes, maybe 5 shear M sizes that we talked about today, are all qualified to PR2. When Cameron looks at the minimum requirements for testing, it really comes down to where the equipment is used and what the application is. Our goal is always to strive for that PR2 requirement to get to the best performing product that's available. But there are some markets where we're trying to, either they're not going to need those physical requirements, or we're trying to challenge towards a certain commercial value of a price point and have tiered offerings where we may go with a PR1 rating. But everything we presented today is PR2 minimum.
Super. Thanks, Matt, for explaining that. I think that'll be helpful. Sam, I've got one. I wanted to go a bit more into depth about elastomers. What's really changed about them to get the performance increases you discussed in your presentation?
Sure. Yeah. Great question. So we're talking about what's inside matters, but it's also what's inside the rams that matter too. So Matt mentioned at the very end that we have the ability to do our own in-house elastomer testing. We also develop our own elastomers in-house. So at our facility out in Katy, Texas, we do have our own lab with our own chemists and team out there, and we build a lot of our elastomers, in fact, all of them from the ground up. So we'll determine through different series of testing with the different elastomer coupons and such what will help us get the specific performance for that product that we're looking for, whether it be a temperature improvement on the high side. So are we trying to get a higher temperature? Are we trying to get it to perform better at a lower temperature? So a lot of the subsea equipment will maybe be more focused on, can it perform at 0 degree Fahrenheit or 30 degree Fahrenheit, versus some of this equipment that sits in surface-based environments where it gets really, really hot, but it needs to hit 300 Fahrenheit for 8-hour hold, which is what we did for the VBR. So the performance enhancements have been driven through the needs of the products and where they sit in the field, and our ability to physically develop those elastomers in-house. It also does depend on the type of elastomer being used. So we can consider using, for example, an HMBR material, which is more robust than an NBR material for some of these higher temp applications. And so that's what we did. We've looked at our baseline performance. Maybe it was, just the wells have been getting more and more challenging. So we need to meet the demands of our changing environment through elastomers and their H2S compatibility. We do also have, I'll make a quick note as well, there's engineering bulletins that Cameron puts out to our customers that can highlight all the different types of elastomers you can get, whether it be for annular packers. We're talking about rams here, but it's the same concept for annular packers, for the BOPs, the bonnet seals. And we do have bulletins that go over all the different capabilities of those elastomers and what we can do next.
Super. Thanks, Sam. We've got a sort of more general question, I would probably say, from Usman. I think maybe more of an overview. Now, obviously, we've got too much detail. I think he's sort of asking sort of what kind of critical applications can this RAM technology be used for. I know one thing, Matt, you went on to was about, sour gas testing. I mean, I know it's quite a general question, but I don't know if one of you wants to just sort of maybe give some little pointers of what you think that the applications could be used for.
Yeah, I think it's a good broad question of where you're coming with this and why we've made some of the changes in the technology we've made. I think if you look at it from the pipe ram world, where we're talking about you're still in a drilling mode, you have a pipe in the bore, and you want to keep it there, and you've had some kind of a well control event, whether it's an influx or a kick or whatever terminology you want to use. One of the first steps, once you've moved off of the annulars, to come down to the ram BOP and shut in and try to capture that pressure so that then you can then circulate out the event and get things back under control. So, like you talked about, Julian, the ability to handle drilling fluids or wellbore fluids that have higher gas concentrations is critical to the development. Also, as Sam touched on with the variable bore ram and the improvement that we've done in higher temperatures and longer holds, that's critical to the operation. And where you see that most critical is that with rig conditions today, there's only a limited amount of space for the BOP to go, the actual blowout preventer, like you see on the right-hand side of the screen, right? The space between the wellhead and the bottom of the drill floor is limited. So we can't just keep adding ram BOPs, which is what you would want to do if you had a fixed pipe ram, because the fixed pipe ram only seals on one size of tubular used in the well, but it does it really well. It's the best performing ram for that tubular size. The variable bore ram Sam talked about allows us to seal on a range of tubulars and do it at all these things. So by having a ram that can go to a much larger range at the high temperatures with the H2S resistance really allows the rig owner or the driller to have more control of the well, to get that situation resolved faster in a more extreme environment and secure it longer while you do the operations required to regain control. So I don't know if that directly addressed the question, but I think that's critical on the pipe ram side. On the shear rams, it's really about deeper, longer wells and higher pressures or higher strength tubulars that are required to drill these longer and deeper wells. Means the BOP just has to be more capable. So the criticality there is, as we want to get to more challenging environments in the drilling world, we need to be secure and safe as we do it. And by improving the capability of the shearing and sealing and how we move those rams together, really, that's what the issue we're trying to resolve with the shearing is.
Super, thanks, Matt. And actually, on that, how many shears can be expected from one set of rams?
Sam, do you want me to get that one?
Sure. You're on a roll.
Okay, thanks, Sam. So officially, Julian, what we would tell you in industry is if you've had to fire a ram in anger, you've had an event where you've had to shear the tubular, the rams have closed, you've sheared, you want to get the well back under control. And then at the next available opportunity, you want to recover that BOP and do an inspection. So officially, the answer is shear and seal. If you've done a shear and seal, recover the rams at the earliest opportunity, remove them from the BOP, and do an inspection. Now, that ram may be acceptable to continue to use. And in historical ram designs from Cameron, some of them could handle multiple shears. With the DSIs, we've seen significant amount of improvement because of the metallurgy that we're using, the blade geometries that we've developed. We're getting more and more successful shear tests using the same rams in a laboratory environment, meaning that I'm doing this in a very well-controlled situation with known fluids, the known condition to the BOP, and I'm doing this shear testing in our lab so we can get multiple tests. The rams keep going, and we inspect them in between each shear to validate that they're still good to do the next test. Generally, we're using those rams over and over because I have a limited number of rams I can use for my qualification process, and customers have a lot of tubulars that we need to validate against. Even when we can shear 7, 8, 9 tubulars with the same rams, the guidance to the customer in the field is shear once, recover the rams, and then inspect them and make an informed decision between the owner of the equipment and Cameron as the OEM for that equipment, and validating whether they're really good to go back into service or not. So it's effectively one in the field, but we know they can handle much more than that.
Okay. That's interesting. And actually, that kind of ties in. We've just heard from Mohammed from Sonatrach, who's just asking, how to determine, the hydraulic pressure to shear different tubulars. I think he wants a bit more of a specific answer.
Sam, you want to handle that one?
Yeah, that one, so there is a calculation. So I guess there's two sides to this that I could tell you. So we can do the calculation for you. So if we have a client that comes to us, for example, and says, I have this combination of tubular, BOP, bonnet, and shear ram, like you think about, I'll push that wheel slide back over. So when you when you look at the variables that we need to consider in order to size your equipment properly, it's the same variables that we need to consider when evaluating shear pressures and shear forces required. So Cameron does have an engineering bulletin that goes over exactly how we calculate shear pressures, so it's not a secret. We do publicize how to calculate the shear pressures. But with that being said, there are certain factors that you would need to know from us or have us perform. Such as the shear constant, which depends on the type of ram involved, whether it's a DSI, SBR, CDBS, so there are going to be some variables that we might have to help you with. But in general, shear pressures are calculated considering the ram designs, and each ram is going to have a different effect on the shear pressure. So your SBR might have higher shear pressure requirements than the DSI, so I think that's the short answer. But there is also a customer service portal as well that if you want access, contact us afterwards, because we can help get you set up on the portal so that you can go in and use it's called the shear calculator, actually. And you can put in those variables that we talked about, put in your inputs, and get an estimate on will your specific configuration be able to meet your needs or not. So if the ram, the pipe, and the bonnet have an output that exceeds the limitations of any of that equipment, whether it exceeds the limitations of the ram and it's not geometrically able to physically shear, or it exceeds the working pressure of the bonnet, if it's most of our bonnets, except for the 5K one Matt talked about, are 3,000 PSI rated working pressure or operating pressure. And if it's calculated to go above that, then we're going to have a red flag on that configuration that says, hey, you need to consider it something else. So all that would be outputs of the shear calculator, which again, that's the second part to my answer. We can do it for you. We can give you access. There's all different ways that we can calculate it, but there is a formula out there for that.
Yeah, and Sam, if I can just add to that answer, that there's one key attribute that you talked about in that shear calculation that we provide, which is the shearing constant. It's a variable that goes in based on the ram and the pipe size and whatnot. And that shear constant is based off of empirical testing. So what I mean by that is that every time we do a physical shear test at one of our facilities, we're recording the results of that shear test. We're maintaining them in an internal database, and we compare the results of the different rams and bonnets and tubulars against each other to develop a constant that helps us be more proactive in predicting what a shear pressure might be. So the benefit to that for the end user is the calculation Sam's talking about. We may not have actually sheared that tubular before, but we have a pretty good idea of what that pressure is going to be because the calculation for shearing is based off of all of the pre-existing real-world physical tests we've done in the past.
Oh, well, I think that's really, really helpful to know. And one thing, obviously, to point out that we'll go back in a second to the last slide, that obviously both Sam and Matt's contact details are there. So anything that's come up during the answers as well as the presentation, please feel free to drop them a line, and I'm sure they can put you in touch and follow up with you as well. We've only got a couple more minutes, so if any more questions that you have out there, please do drop them in. I've got a few more still to go, but so Sam, I want to talk about pipe rams and what is hang off and how do you prove the capability?
Yeah, so sure, we did touch on that. Actually, we can leave the context slide up for now. I'll just give a short answer on this one, but hang-off capability, like I talked about, our 18-inch VBR achieved 1.1 million pounds on the largest pipe range, which is quite impressive. But for those in the audience that don't know what hang-off is, it's something that happens during regular operations. There might be instances where the operator needs to set the pipe down to take the weight off of the rig for other operations or in advance of a planned shear. So for the BOP, the BOP assembly itself, that means that the ram block must be able to engage with the pipe, and that interface is between the pipe and the tool joint. So in the case of a fixed pipe ram, you make that interface to seal and hold the load of the pipe at that tool joint. In the VBRs, though, the variable bore rams we talked about, it gets a little bit more complicated, which is why it's impressive when we can do it, because we need to be able to seal on a wide range of tool joint sizes. And hang-off is one of the tests that we do as part of API 16A 4th edition qualification. So we'll hang off on those sizes and make sure that if there's interface with the ram block or not. So if you get into a situation where the tool joint is only hanging off on the packer itself and not the ram block, this will greatly affect the hang-off capability. So the way we prove the capability is in that lab testing that we keep going back to. So we actually built a hang-off fixture in our labs that allows us to change pipe sizes, whether it be 3.5, 5.5 inch tool joint configurations associated with that pipe size to validate that the VBR, for example's capability. So during that testing, we'll push down on the test manual to simulate the weight of a tubular because we're not using an actual rig. So we'll push down on the test manual to simulate the weight of the tubular, and then we'll also apply pressure from below to simulate wellbore pressure being applied as if it was a real world test.
Super, thanks, Sam. Now, Matt, you were discussing tandem booster bonnets, and what changes to a company's BOP are required, would you say?
That's a great question, Julian. Let me pull that slide back. But the key driver here is that everything we've talked about today is available to mount directly to the BOP you may have today. In the case of the 5K tandem replacing the legacy existing product that's out there, it's really plug and play with the exception of the controls system. So the BOP itself doesn't physically change. We unbolt the existing bonnet, bolt up the new one. We just have to run new hoses or new tubing to the right functions on the bonnet. It's not physically easy to do because you have to get out there and make hoses and tubing runs and whatnot. But from a performance standpoint, it's a relatively simple step. And with an 18 3/4 15K subsea BOP stack manufactured by Cameron, the majority of the control system is rated to 5,000 PSI. So with the old product, we were running it at 4,000, which meant we had to step down and run through an extra regulator to get the pressure down to that max rating of that bonnet. And so by going to the 5,000, we can remove that bit of the control system and simplify the process, makes it slightly less things you have to worry about and run through. But effectively, it's backwards compatible. You bolt it up, you change some hoses, and your system runs forward. The control system doesn't even really notice that it's different once you've made those plumbing changes.
Great. Well, that's really interesting here. And obviously, both of you mentioned, and outside the calculator, and the focus on the R&D side of this, and how important is that? Because I think you've really been emphasising that with the unique capabilities that you can offer through that.
Yeah, I think the key. Or go ahead, Sam. I'll let you go first.
No, I mean, I think we could both answer that one. It's the foundation of why we're here. I mean, it does take a lot of iterations to get it right, but we need to be able to test everything to make it field worthy. I mean, what we do in the lab, especially with temperature testing and the hang off and stripping testing, we didn't really talk too much in detail about how we test, but how we test matters just as much as the output, because we need to simulate real world conditions and make sure it's suitable for service. So I think it's fundamental to all of this. It's part of our at Schlumberger, we have a NPD, new product development process. It's incredibly structured with key milestones. And we can't release a product until all the boxes are checked, until everything's cleared. And that's a whole nother hour-long presentation in itself about how we do that. But it's definitely fundamental.
Yeah, I think, Sam, the key driver, Julian, to that is, we know the world is changing, right? The needs are constantly evolving. Heavier, deeper, tubulars, longer step outs drive that need. We're seeing environments where we have to go to higher pressures and higher temperatures to achieve get the oil and gas that we need back for the world to go. So really driving what are those requirements. Sam and I spend a lot of our time engaged with our customers, both internal and external, right? Just the different parts of Schlumberger that use our products, as well as all of our external customers around the world, to understand what their needs are, what they're trying to accomplish, and then conveying those requirements back to the engineering team and setting forth on the right path. Some of those developments we talk about for a long time, and it takes a while to get there. Other ones, like Sam mentioned, with the 13-inch DSI, we get there in a very short time because we have to. Right? There's an immediate need for that product. We run through and we spearhead that project as an emergency kind of development. So it really just depends on where it goes. But the core driver is innovation and improvement in our product portfolio is always imperative to be able to respond to the customer's needs. And that's what we spend a lot of our time doing, and it's pretty interesting.
Oh, well, that's great to hear. And obviously, we're just going to wrap up in a couple of minutes. And just to remind everyone again, Matt and Sam are here, if you have any further questions. I think it's been a really interesting webinar, really got into the nuts and bolts of your RAM technology and just getting the understanding of why you both are so enthusiastic about it and what you're doing. So, yeah, I just want to thank all of you for joining us in this last hour as we've, looked in depth at Cameron's RAM technology. And we really learned a lot about, the latest shear and seal advancements for both onshore and offshore environments. And it's clear that this is such, an important topic. And as you said, Matt, there about, innovation and looking forward, we're in a dynamic, changing energy landscape. And I think this is going to be quite key to that. I just want to thank both you, Sam and Matt, for joining me and giving me your time.
Julian, thanks for having us. It's been great talking to everyone this morning. And as you noted, if you have any questions for Sam and I about Cameron's RAM technology, please drop us a note. Our emails are there, and let us know, or reach out on LinkedIn or any other way you may know how to get in touch with us. Yeah?
I agree. Thanks, everybody.
Yeah, and just for everyone's understanding, you'll be able to rewatch this webinar on demand, which we'll make available in the next 48 hours. So do look out for an email, and then you can watch it then. Thanks all for watching, and I hope you have a good morning, day, or evening. Stay safe, and do keep following us via our website or social media for the latest industry news and insights. From all of us here, goodbye.